Hello everyone, my name's Mark Hill and I'm here to talk to you today about an extension we're adding to our next generation of RISC-V microcontrollers in Huawei, which we've called the trusted execution state. And the primary motivation for which is to provide a mechanism to do lightweight secure function calling. So first of all, a bit about me. My name's Mark B. Hill, to distinguish me from the Professor Mark D. Hill, who's a professor of computer science at the University of Wisconsin, which I'm sure you're all far more familiar with than me. So just to make it clear, I'm not him. My background is that I spent 18 years at STMicroelectronics and associated companies working on processor development and architecture and modeling, application analysis and benchmarking, and design flows, and also a bit of design management. In 2014, I joined Huawei. I was the first employee and the lead engineer at the new Bristol R&D Centre. And our primary focus at that time was to develop a multi-threaded ARM v8. Since then, we've become more biased towards RISC-V development. We're particularly interested in security in devices such as IoT and set-top and digital television, but potentially everything we do has a much wider applicability. So what's the rationale for this extension? So there are several trusted execution environments available for RISC-V already, and these such as multi-zone or keystone, and these all rely on using machine mode as the most trusted privilege level in the machine. Isolation between user tasks is achieved by reprogramming the PMP on a context switch, so every task that's running is limited to its own memory space. But for us, that introduces some security weaknesses because the really trusted, secure services that we need to provide, like attestation and signings, they're running in the same privilege as the kernel code, which is there to manage the tasks, both the trusted and the untrusted tasks, interrupt handling and exception routines, and potentially some device drivers in there as well. All these things potentially provide backdoors to access to secure data or the trusted services. So fundamentally, we're worried about violating the principle of least privilege, of just allowing things which need access to a certain functionality to get access to it. We'd be much happier with much finer grained isolation. All this additional code makes it hard to ensure that the security loopholes haven't been introduced. For example, buffer overflow susceptibilities, which allow or ABI abuse, allowing an attacker to get control of the machine at a higher privilege than they should be allowed to. And as the code size increases, you've got it's less easy to apply formal methods and formal checks of the correctness of the code, and you're increasing the pool of code that's there to build gadgets for return-oriented and jump-oriented programming style attacks. So as well as that aspect of it, the other thing that we want to do is provide a very efficient mechanism of getting between the untrusted state and a more trusted state. Now this currently in typical TE solutions involves a change in privilege, which you do, for example, through a system call, but there's quite a lot involved in doing a system call. You need to prepare your system call stack. You go for a single entry point by executing an eCall instruction. On the other side, you've then got to decode that call ID and work and then pass it on to whichever piece of trusted code is going to handle that operation. And then, having saved all that thread state, you've got to restore it and do an MRET to go back to it. So it's quite heavyweight. If you think about scope, so I want to emphasize that this extension is intended for sort of low to medium value assets where we're happy for the security features we're adding to actually be resident on the same CPU as the untrusted code. For the very highest value assets, we would still have solutions where we have a separate dedicated CPU, which my colleague Terry Kerr, for example, talked about at the last RISC-V summit, which allows us to have a fully isolated and physical separation between the security functionality and the untrusted activities on the CPU. So, for example, the aim is to protect those trusted keys, that secret information, keep it separate from everything else that's going on in the machine. We accept, particularly if we allow untrusted machine level access, that there's loads of opportunities for the machine to be crashed, or for denial of service type attacks to be applied to the trusted world. We're not so concerned about that. As I said, I'm concerned here is to check that secure data in this environment. And the other thing I would say is that this talk is primarily focused on how this technology could be applied to an MCU where we're assuming that we've just got an M mode and a U mode, maybe an S mode without an MMU. So as I say, we've coined this extension the trusted execution state. On the left-hand side of this diagram, this is the standard base ISA that you'll all be familiar with in terms of the privilege levels that RISC-V provides. And then on the right-hand side, we created a new state called the trusted execution state, and we provide mechanisms to transition between these through calls and returns and jumps and returns, going in these horizontal transitions, and then the vertical transitions we'll use this more conventional, the standard sort of interrupt and exception mechanisms that RISC-V provide. There's also a way of going diagonally from an untrusted user state to a trusted machine state, but there is no way to go directly from a trusted user state to an untrusted machine state, because that requires special pre and post handling. So the way that we demark which regions are of the address space are trusted and which are untrusted is by an extension to the PMP, the physical memory protection unit, which is part of the RISC-V base ISA. And then we add an extra bit into each PMP entry, which are called the T bit, and that tells us whether it's a trusted region or an untrusted region. So in this example, we have trusted regions called A, B, and C, and we have some untrusted regions called D, E, and F. And the basic rule is that if you're executing in an untrusted execution mode, you can never access or execute any code which is within a trusted region. So when you're in a trusted state, you're still allowed to access untrusted data because you need to be able to get information from the untrusted world. And but as soon as you attempt to execute code which is untrusted, that your privileges, your trusted permissions are automatically revoked. So, so entering the untrusted world, well, as I say, we don't allow any sharing of code between the trusted and the untrusted worlds. So this helps to avoid situations where trusted code is tricked into executing the attacker's untrusted code, because any code which is placed in the untrusted world cannot be executed in this trusted state. What happens, as I say, is you immediately, if you go through a jump which causes a transition from a trusted region to an untrusted region, that jump is permitted under some constraints, but your permissions for access to anything trusted are immediately revoked. So as I say, there are some constraints. So only jumps with no link register specified, i.e. by specifying X0 as the link register, are permitted. And if there's an attempt to transition via any other mechanism, you get a fault. This is primarily to avoid mistakes in the software whereas say a trusted piece of code calls an untrusted function and forgets that it's not a trusted function, not a trusted function, and needs to should have put a wrapper around it. Again, something I'll discuss later. So, easy enough to get out of trusted execution state. So the big question, of course, is, well, once I've jumped out of it, how do I get back into it? So the way that works is that we define something called the TESLvec, and the TESLvec is defined by 2 CSR registers, a sort of low watermark, so the base address, which goes into into this CSR register, and another one, the TMES top, where the top of the TESLvec region is stored. And what we do is we have this window of pointers, and it looks a bit like it's like a jump table that you'd have, say, as is implemented in the click, for example. It's an array of entry points into trusted code. The TESLvec itself must be in a trusted region, and in terms of the privilege level, you can place it at whatever privilege level you want to permit. So if you only want to allow machine mode to access a TESLvec, then don't give it user privileges. If you want to make the sort of untrusted user to trusted user calls, then you make it visible. Give it trusted user permissions. Okay, so once you've set up your TESLvec with pointers to all of your trusted functions, your entry points that you're going to allow into your trusted world, you can make an untrusted call to that trusted function by using a conventional call instruction, which actually, instead of calling the function directly over here, actually calls the TESLvec here. So we come along here, we pick up this entry, we read the contents of this entry, and that redirects us out the other side, switches us into a trusted execution state, and at the time, and it also, as it does that, it records what the trusted execution state of the caller was. I'll explain why we do that in a second. So we go across and we call the trusted function. We execute our trusted code. And then when we're finished executing our trusted code, we do a conventional return instruction. And because we're returning to code which is untrusted, automatically we'll get a revocation of trust and we'll transition back to untrusted execution. So there's a little example here of the logic for that. So just to remain in trusted execution state, we need to be in trusted execution state, and we need to, in this case, do a PMP lookup on the return address, and we check the T-bit for that PMP entry to make sure that it's got the T-bit set. If it hasn't, then we're always going to go back to untrusted state. There's a second option here, which is instead of using conventional return, we can define one new instruction, which is called the TRET instruction. And what the TRET instruction does, it adds an extra clause into that expression. So as well as having to currently be executing in trusted execution state and the address matching in the trusted region in the PMP, we also confirm that the caller was trusted or untrusted. So if you want to stay, this means it is possible to call through the TESLvec from trusted code to another piece of trusted code. And this extra clause here ensures that if the call wasn't from trusted world, then you'll get an automatic, that this will be an extra check, an extra guarantee that you're forced out of trusted execution. The reason you might want to do this, although it's not necessary for the mechanisms to work, it gives you an additional bit of security if you're paranoid that perhaps some ABI abuse has corrupted the control flow integrity of your trusted function. Of course, so when we're transitioning from trusted to untrusted execution, we need to be very careful not to leak any information from that trusted world back to the untrusted world, either through the general purpose registers on the stack or through by writing into untrusted structures and so on. So we'll provide some hardware mechanisms to assist with that. The purpose of, in theory, all these mechanisms could be done in software, but the hardware mechanisms are there for a number of reasons. One is as a performance enhancement. For example, we need to zero a lot of registers when we transition to make sure that we're not leaving anything useful in the registers. We need to, so doing that automatically, we can improve the performance. There's also, we can secure it by doing it hardware. We make sure that we eliminate the risk of, if we're doing software, that we kind of forget to do it in software and we expose a potential security hole there. And the third reason why it's used to have the hardware assistance for this is just the usability. It means that the code can be written in C, the trusted functions can be written in C. We don't need any handwritten assembler entry-exit sequences. It's generated by the compiler. We point to it out of the TESLvec and it just works. So the mechanisms we need for this to be effective is we need to shadow some of the registers. So we shadow the stack pointer. So we have an untrusted stack pointer and a trusted stack pointer. And we switch between them when we switch between the untrusted and the trusted world. We also shadow the global pointer and the thread pointer, which, although we don't expect them to be changing dynamically, the untrusted world could potentially confuse or corrupt the trusted execution by modifying these to an unexpected value, so that when the trusted code accesses a global object, it sort of writes it in an untrusted region of memory instead of a trusted region of memory. So we have shadows of those. And then in addition to that, we do some automatic clearing of subsets of the register file. So which registers get reset or cleared depends upon the type of the instruction that's causing the transition. So if it's a jump, then what we need to do is to clear all the temporary registers and the save registers. If it's, we leave the argument registers in place because we are going to use those to pass arguments to our untrusted function. The return registers, if we're doing return, then we can basically clear all of the temporary registers and the function argument registers, apart from the ones used for function return. We don't need to worry about the saved registers because the code that we're executing in the trusted world should be following the standard ABI, which will restore saved registers to the values that they had on entry to the trusted function. So all that the untrusted world sees is the values that we put into those on entry, so that's safe. And if there's any other kind of jump type operation, for example, a condition branch, we just cause, or a core function call, which we mistakenly made from the secure world, we just force a fault at that point. Okay. So here's an illustration of a really simple way, a simple illustration of how the TESLvec might be used to just provide some simple security services or trusted functions that can be used by the untrusted world or by the trusted world. So we declare in this little header here some our trusted functions, 1, 2, and 3. What we do here is we actually do a bit of renaming so that if this header is included by the secure code, it uses these names, SC1, SC2, SC3. If it's included by untrusted code, then the untrusted code has to they get renamed to 2SC1, 2SC2, and 2SC3. So whether it's secure code or untrusted code or trusted code, the calls to those secure functions can look the same in terms of the C code itself. But what's going to happen if we are, if this is running an untrusted world and we're running untrusted code, these are actually going to be, these macros here are going to relabel them to 2SC1, 2SC2, and 2SC3, which in fact are entries in this little TESLvec table here that we've generated with this bit of assembler here. We've got a define here for every TESLvec entry, which we should just apply the function name to, and it adds the prefix onto that to declare a label, and then it declares an entry for that TESLvec entry and that entry contains a pointer to these trusted functions up here. And then in our initialization code, we'll have to initialize the CSR registers with the TESLvec base and the TESLvec top. Okay, so I hope that's clear. And then a second example here of how we would use the mechanisms that the trusted execution state provides to perform a lightweight untrusted function call. So I'd say this is a little bit more complex. So every call to a trusted, untrusted function needs to be wrapped if it's going to be called from the trusted code. And this wrapper is best performed by using a C macro or something that generates a wrapper for you automatically to ensure that all the steps needed are implemented and you haven't missed anything, and to ensure a consistent implementation of the wrapping mechanism. So obviously a new feature like this needs a lot of careful review by a lot of different teams, particularly the groups doing software development. So in order for them to be able to evaluate it, I've implemented the extension as a QMU feature, which uses the standard mainline QMU model, but on the branch I've added a trusted execution state extension, which allows you to, when you select your CPU, you can also select that it's got this ZTES extension, there's actually another extension called ZTES multi, which I'm not going to talk about today, I haven't got the time. And I've also, to demonstrate how to use the various features of the extension, I've developed some sort of demo codes which are based on the RISC-V Pro code, which is available on GitHub. This is a useful way for people to evaluate the feature, because they can take their existing OS codes and they can just add some trusted functions into it to provide some sort of basic trusted services like signing and attestation, with very minimal changes to their OS kernel, assuming that what they do and what I typically expect in the first use case is that all of the OS code, be it a RE or be it a T, is actually run in the standard base ISA mode, and so effectively the untrusted mode, and we only use the trusted mode just for those very few features, those trusted services, like I say, like the signings and attestations and access to the hardware unique keys and things like that. Okay, so that is the complete presentation. I hope you all found that interesting. And I think the plan now is that we go live and I'm able to answer your questions. Thank you very much. Goodbye.